Artificial intelligence models are growing at a rate that breaks traditional computing infrastructure. The total parameter count of these models is exponentially dividing and doubling, forcing engineers to throw massive amounts of physical hardware at the problem. To maintain performance, data centers rely on two brute force strategies: scaling out by linking thousands of processors together, and scaling up by making individual GPUs mathematically faster. Yet, despite deploying this massive scale, the compute cores are starving. This visual features a Gantt chart, a timeline used to track the start and duration of specific tasks. This chart tracks the execution timeline for DeepSpeed, one of the most highly optimized software frameworks for AI. Despite the advanced hardware, the actual compute utilization sits at a mere 7.7%. The massive block taking up the rest of the timeline is memory stall time. For the remaining 92.3% of the time, fast GPUs sit completely idle, waiting for a trickle of data to travel up a deep hardware hierarchy, from physical storage to local memory. Adding faster, more expensive processors to this specific architecture is mathematically useless. If the processor spends 93% of its time waiting, increasing its mathematical speed only means it finishes its calculations sooner and returns to a state of idle waiting. The bottleneck is entirely in the wait time. The standard industry response to this latency is to construct wider physical pathways. Engineers build high-speed interconnect cables, like NVLink, to tie GPUs together, or they insert isolated ultra-fast storage tiers, like Intel Optane, to bridge the gap between RAM and physical disks. This strictly hardware-centric approach fails mathematically due to Amdahl's law. Amdahl's law is a formula demonstrating that the overall speedup of any system is strictly limited by the specific parts of the task that cannot be sped up. If the data access time remains fixed, infinitely increasing the compute power yields almost zero system-wide improvement. This physical disparity between rapid processor speeds and lagging data access times is known as the memory wall. Over the past 4 decades, the execution speed of processors has increased vastly faster than the time it takes to move data out of memory. Breaking the memory wall is not a matter of increasing raw device capacity. A system can possess infinite storage space, but if it requires 5 million clock cycles to retrieve data from the deepest drive, the processor still starves. The true metric to solve for is minimizing system-wide memory stall time. A GPU's peak theoretical speed is an illusion if the data flow cannot be continuously sustained across the entire system. Raw physical interconnect speeds and standalone storage tiers are mathematically insufficient on their own. Without a software-defined strategy to overlap these exact data requests, the hardware will always be waiting. To eliminate this wait time, the architectural thinking must shift away from sequential memory access to fully concurrent access. This diagram displays the formula for CAMAT, or Concurrent Average Memory Access Time. CAMAT is a mathematical model that calculates the true performance of a memory system by factoring in how multiple data requests can be processed at the exact same time, effectively overlapping the delay of pure misses. In a traditional sequential failure, a processor checks its fastest, smallest memory, the level 1 or L1 cache, and if the data isn't there, it pauses. It then checks the slightly larger L2 cache, pauses again, and moves to the L3 cache. Each miss adds a distinct, linear step of delay that accumulates into a massive stall. The CAMAT model illustrates that if you overlap these pure misses, the total execution time drops. Instead of waiting for one search to finish before starting the next, the system forces multiple tiers to search for different pieces of data simultaneously, which causes the sequential steps to slide horizontally and compress the total wait time. The practical implication is that an L1 cache miss can be completely hidden by overlapping it with a slower L2 or L3 miss elsewhere. Because the wait times occur in parallel, the total system-wide stall time plummets. CAMAT proves that the physical barrier of the memory wall is actually a highly complex, solvable scheduling problem.
While CAMAT proves that latency can be hidden mathematically, raw equations cannot move data. Executing this theoretical concurrency on physical hardware requires a specialized software middleware. This diagram shows Hermes, the direct software realization of the CAMAT mathematics. Hermes is a multi-tiered, distributed input-output buffering system situated directly between the compute processors at the top and the physical storage drives at the bottom. Hermes utilizes two core mechanisms to execute concurrency, starting with vertical concurrency. Instead of checking drives sequentially, Hermes accesses the rapid L1 cache, the larger dynamic random access memory, or DRAM, and the deep non-volatile memory express storage drives all at the exact same time. This vertical overlap actively blurs the strict physical boundaries between volatile, rapid memory and slower permanent storage arrays. When that local vertical hierarchy is completely exhausted, Hermes triggers its second mechanism, horizontal concurrency. Hermes dynamically reaches across the network to fetch data from the memory pools of adjacent computer nodes. If a local vertical drive is too slow, it simply grabs the data laterally from a neighbor's fast memory, bypassing the local bottleneck entirely. Integrating this horizontal and vertical routing creates a massive, unified logical memory pool out of disparate distributed physical components. Hermes provides the physical infrastructure to achieve total concurrency. But a buffer is useless if it doesn't know which specific pieces of data to move. Intelligent data routing is required to match the demands of the AI application to the physical concurrency capabilities of the hardware. This logic is handled by two specialized layers in the software stack, IO Warp and Labios. Labios functions as the profiler. It actively monitors the AI application to map out its specific, unique workload and data access patterns in real time. IO Warp takes that profile generated by Labios and uses it to map the optimal data flow pathways directly into the Hermes buffer. Together, IO Warp and Labios act as the brain of the operation. They ensure data is surgically pre-positioned exactly where the GPU needs it, rather than moved blindly through the system. The data lifecycle begins long before it reaches that routing layer. Training AI models depends on the continuous, massive ingestion of external log data. Chronolog is a specialized ingestion engine built entirely to handle this high-concurrency external data. Log data presents a unique architectural challenge. It consists of append-only streams, meaning new data is constantly added to the end of a file without modifying existing entries, and this format requires strict chronological ordering rules at a massive scale. Chronolog solves this by utilizing AI to predict timing, optimizing and staging the data before it ever hits the compute layer. Chronolog structures the raw chaos of external data. It ensures that the internal IO Warp and Hermes stack always receives a perfectly optimized, ordered stream. This diagram illustrates the complete unified data flow architecture, from external ingestion at the base to final compute at the peak. When a cycle begins, Chronolog strictly orders the massive incoming data stream. Immediately, IO Warp and Labios analyze demand, charting the optimal multi-tier path. Hermes then executes the CA-MAT mathematics, shuffling data concurrently across vertical tiers and horizontal nodes, bypassing bottlenecks to flood the GPU. This brings us back to the Gantt chart execution timeline. With the full stack running, the massive memory stall block shrinks dramatically, and the active compute block expands rapidly past that initial 7.7% mark. Obsessing over the peak speed of individual hardware devices is an architectural dead end. True system performance in modern artificial intelligence is defined entirely by the ability to maintain continuous, overlapping data flow to the compute layer. Integrating memory and storage into a single, software-managed continuum is the only mathematically sound way to break the physical limitations of the hardware. The memory wall is no longer a terminal physical limit. It is a structural scheduling challenge, one that we now have the full-stack architecture to solve.